the organizers. So this today will be the first of a series of 3 talks. So the first today I will talk about the H principle for wrinkled submersions, but I won't finish today, so it will somehow carry into the second talk tomorrow, certainly. And then at some point I want to say a little bit about wrinkled embeddings, and finally I want to talk about generalized Morse functions and do some theorems on generalized Morse functions. So that's the rough plan. Okay, so and one goal of today's talk is, remember that Yasha told the story yesterday that this was Gromov's explanation to him about what Hirschi-Mersenne theory was really about. Yeah, but this picture has not really appeared so far in the talks that we've heard, and it's going to appear in the talk. Okay, so let's recall some things from Dennis. So we have so the H principle holds for maps, let me say for immersions. Now, I'm not going to try to stick to Alvarez's notation. It will be impossible for me. So for me, the source manifold is V, it has dimension N. The target manifold is W, it has dimension Q. Don't ask me why, but this is somehow what it ended up being. Yeah? Okay, it was not my choice. So, so those are the dimensions of those manifolds. So, and we have immersions. And the H principle holds if V is open. As Dani explained, in fact, thank you. In fact, it's a special case of a more general H principle, which over an open manifold holds for open invariant differential relations. It also holds for immersions if V is closed. And the dimension of V, i.e. N, is strictly less than the dimension of the target manifold. Then it's still fine. But today's topic is submersions and completely fails for submersions. So it does not hold if V is closed. So I could add here, it holds for immersions and submersions if V is open, because submersions is also an open differential relation. So that is still fine if the manifold is open. But as Dani already explained, the micro extension trick doesn't work for submersions, so we cannot get it from an open manifold to a closed manifold of well, and codimension is anyway not the good thing to do for submersion. Yeah, so so it fails if V is closed. And here's an extreme case, which will be, in fact, probably the main example for this whole talk. Let's take the target manifold just to be one-dimensional, so it's as extreme as can be. So a function from a manifold to R can never be in submersion. Submersion would mean that its derivative is nowhere 0, right? So it cannot be a submersion. But what we're going to see is that you can make it a submersion almost everywhere, except for some very controlled singularities that I'm going to explain. So, but holds if we allow some very special, well, I wouldn't even call it critical points, but some very special critical points. Yeah. Points where it's not a submersion of a very specific nature. And well, in this example, we kind of have an idea what critical points we should allow for a function, because a function generically such a function is a Morse function. Yes. So, which means that a function has only non-degenerate critical points. So, okay. Now, so this is something that even for this example we want to allow. We want to at least allow critical points which are non-degenerate. So that's the first type of singularity that we need to allow. Now it turns out we need to allow a little bit more. So here's points where it's not submersion. Yeah. But if we look at a one-parametric family of functions, so generically in a one-parametric family, we'll see the following behavior. And let me maybe, so it will be, so this is the variable and this is the parameter, say. So it depends on two variables. And we have typically the following behavior. Now let's actually analyze this, because this will be fundamental for everything that comes. So let's just analyze this specific case. So what is happening here? Well, if I can draw it as a movie of functions, depending only as of z on z with value with parameter y. So if y is negative, then this is also something positive times z. So the derivative is always positive. So this function has no critical points. Now at y equals 0, well, we can just draw it. Yeah, we know it all. And at y bigger than 0, we'll see this picture. So those are two non-degenerate critical points. So this is Morse. Well, this is also Morse. But in between, there's this moment, this critical point is not Morse. Yeah, so the second derivative also vanishes, but the third derivative doesn't. So it's some of the smallest deviation from being Morse that we can see, and this is sometimes called a birth-death critical point or an embryonic critical point. Yeah, and so embryonic refers to this thing as an isolated function. Birth-death, if you think of this whole family, you see that going from here to here, two non-degenerate critical points are born. A pair of critical points is born, and going from here to there, they disappear. Yeah, so that explains the terminology. Let me. Okay. So how does this generalize? So what? And it turns out that those are the only two types of critical points that we need to allow, and these will generalize to something called folds, and these will generalize to something called cusps. Okay, let me talk a little bit about. By the way, ask questions. Yeah, I feel people are not asking enough questions during the talk. Yeah, so ask questions, interrupt me anytime. Okay, so what is the general situation? So let's talk a little bit about the very simplest cases of the so-called Tom Boardman singularities. We have this function f from v to w, so we can talk about its differential at some point. So this goes from the tangent space of V to the tangent space W. And we can ask, so being a submersion means that it's surjective, being an immersion means it's injective. We can actually treat both cases on the same footing, and that will actually turn out to be useful by asking, when does it have the maximal possible rank? So let's remember this has dimension n, this is dimension q. So let's define the co-rank of df to be the maximal possible rank, which would be the minimum of n and q. Yeah, so the maximal rank is the minimum between n and q. That's the maximum rank it could have. And then we subtract the actual rank, and that we call the co-rank. So it's somewhat the deviation from having maximal rank. Yeah. So I should take this at one particular point, because this is changing from point to point. Yeah. Okay. So okay. So for immersions and for submersions, the co-rank is 0. Yeah. So then let's define sigma k of f, those points V, say in V, such that the co-rank of the differential f at V is equal to k. Now, it's an exercise in Thom's transversality theorem that these things will generically be manifolds. And so this is inside of V generically submanifold of a certain dimension, which one can work out. And I don't want to do in general, I will do it in a special case if we need. Okay? Now, once you have that, then you can look at F restricted to this submanifold. This is now a map from this submanifold to W. Now this has different dimension, yeah? So there's lower dimension, but still, it's a map now between two manifolds of certain dimension. We can again ask, does it have the maximal possible rank? So we can define its co-rank. And we can define we can define sigma aj of f to be the points V in sigma k of f, where the co-rank of the differential, well, I should really, yeah, okay, it's the same, it doesn't matter. Vf restricted to sigma k of f is equal to j. Yeah. Okay, so again, generically, this will be a submanifold in sigma k of f, and you keep going. Okay. Now there's a more fancy way of expressing everything in terms of some particular stratified subsets in the jet spaces, and then these are the pre-images of those subspaces in jet spaces. And Thom's transversality theorem tells you generically you can be transverse to all those subspaces in jet space, and then you get this picture. Okay, so we wanted to allow the mildest possible singularities. So folds would be something which corresponds to sigma 1. So the co-rank or the rank of sigma just drops by 1 compared to the maximal possible rank. And moreover, afterwards, once you restrict to that, it has maximal possible rank. Okay. So this is this we would call a fold. And I will give a local model. Yeah, maybe let's do it right now. So you can show that a local model for that is the following.
So is n greater or equal than q here?
So let's now assume that n is strictly greater than q. So I want to talk about submersions. Yes. So I'm doing a terrible job in running back and forth. Sorry.
I'm also getting better.
Do you insist on strictly?
Yes, I want to. For this, probably. Well, for this, I think for now it doesn't matter. It will ultimately, but for now, I can allow it to be equal. So let me write the local model here. Will be, let's call y in R q minus 1, comma x is the remaining coordinate. So it's R n minus q plus 1. I split the coordinates in this way. And then locally, I just map it to y. And then I have one function left, and I just take some quadratic form here, where q of x is a sum. Well, x goes from 1 to wherever it goes. So j going from 1 to some index s with a minus sign, minus xj squared plus sum over j equals s plus 1 to wherever it goes, x j squared. So I take a standard quadratic form, so that of some index s here. So this q depends really on s, and it depends maybe on the number of variables I have. Yeah. So it's a quadratic form of some index in this last coordinates. And how do you think of this? So let me draw the case where y and x are both one-dimensional. So let me draw y here and x here. So it's so one way to think. I'll try to do a three-dimensional picture. So we have now this additional direction. Let's call this direction u. So let me try to draw a 3D picture. So u is upwards. I draw y to the right. And I draw x maybe down here. And then, so u, this is the last coordinate. This is now some quadratic form. Let's say I take x squared. Yes. So, what do I want? Yeah, I think it's so it's this kind of function, and then it's in the y direction. It goes like this. So it's a quadratic function in the x direction, translation invariant in the y direction. If I just draw this as a function of just y in three-dimensional space, and then we forget about the x coordinate and we project it onto yu now. So what do we see? If we project it onto yu, then we just see the upper half plane. Now you see why I drew a three-dimensional picture, because if I just tell you it's a map from here to here, which is doing this, you don't see a fold. Right? You see a fold if in between you put the three-dimensional picture, then you see that in three-dimensional space it looks like you take this plane, you fold this plane. Okay, that's why I got this. Right? You have a map from the plane. Now you fold this plane, and then you project it into this direction. Yeah, that explains why it's called a fold. Okay, now I can squeeze the now cusp is the well now there would be two possibilities. We could either say we want to allow co-rank 2 here, or we want to stick to co-rank 1, but we want to somehow allow a 1 in the next stage of the Tom Boardman classification, and that's what we want to do. So cusp will be sigma 1, 1, 0 of F. Okay. So what does this look like? I'll also give you the local model. So the local model at a cusp would be, we take again y in R q minus 1. I separate out another variable in R, and then there's remaining variables in R n minus q. And we map this one to, again, we put a y here. Maybe I should have mentioned it. You see that the co-rank can be at most 1. Yeah, because on q minus 1 coordinates, I'm just mapping y to y. So this is it's giving you already co-rank q minus 1. So the only way it can drop is where all the derivative here, all of these derivatives are 0. Yeah. And now here we're doing something similar. This ensures already that we have co-rank at most 1. Now we have one more function here to ask for, and we put d cube minus yz, precisely this family of functions that we had before, which is somehow hidden now. And well, then we need to still do something with add a quadratic form in the x coordinates.
Is it the norm of y or?
Okay. Sorry, I should take. I take one component of it. Let's take the first component. Thank you. Thank you. Yes. Yeah. So I take one component of y here, which it is. Okay. So and you can compute yourself, yeah. So I think it's actually a fun exercise which I'm not maybe going to do, yeah. So to compute that this is really of the type 1, 1, 0. So you need to somehow compute first, second, third derivatives. But the good thing is you only need to compute second derivatives where the first derivatives already vanish, and then so on. So it's actually not so bad. You can do it as we go. Yeah. Okay. So what does it look like in the simplest case where I have only one coordinate here and one coordinate here? I forgot about the x. So let me again try to draw it here. We have y and this particular coordinate z now. Again, I want to call this new coordinate u. I want to draw a 3D picture now. So it's u, y, and z. Okay. Now, what is it going to look like? I need to draw the graph of this function. I should take y1 here. Yeah. So it's just the first coordinate. Yeah. So I need to draw this function as a function of two variables, and if I'm not mistaken, it's going check which way it goes. Okay. Probably put minus that here. Yeah. So then I think the picture would be something like this. down and up in this direction at positive y. And then as you go, well, I think the singularity should actually be end up at y equals 0. Okay, let me try to do it accurately. I move this to the right. It's really at positive y. Now we go into y equals 0, and we're going to see this kind of behavior, and that's okay. So you can close it up like this. So it's like I'm not going to do it to this poster, but it's on this side. I do a double fold that I can nicely do, right? But then I somehow want to make it go away as I go from the edge to the inside. Yeah, I make this double fold go away through this singularity. But at that point, the paper is going to. Yeah. So I'm not doing that. So here's some special point which is somewhat more singular than the others. Yeah. And now we project onto. So we go here, and then we project onto the y1, sorry, onto the y1 u plane. So what we're going to see is we're going to see this cubical cusp here, and when we project, we see that somehow over this region here, it's threefold covered. And over the other part, it's simple covered. Yeah. So if you project, you see that there's the points here have three images, three pre-images, and here they have one pre-image. Yeah. So and somehow it jumps across this curve, which is describing a cubical. So that's the picture. Any questions on this? Okay. All right. So now we're ready to move ahead.
Sorry, can I ask one thing?
Yeah.
This local model is like a local model around this sigma 10 in B, right? So if you
Yes.
so the sigma 10 is the axis in this picture.
The sigma 10 is the axis in that picture. The x is equal to 0. Yes, I can add it. This is a sigma 10, and also here the sigma 110 is this point in the picture. Yeah, and maybe I can add this part. Okay, there's a part which is mapped onto this where x is equal to. Okay, now let me know. There's some other question?
That's your question?
Yeah.
Is it hard to see where the sigma 10 points are in that picture?
Yeah, I was just wondering. Okay, so what did I need to compute when is this derivative 0. So this derivative is 0 if x is equal to 0. Because here is a quadratic console, so the derivatives just give me x, right? So okay, but x is not in this picture anyway, so it doesn't help. So I need to compute this derivative. So let's do it. So, and let me, for the fun of it, because I'm doing it later anyway, put a 3 here. So then the derivative by z is going to be 3z square minus y. And that equal to 0 is
Tilted to the right.
y is z squared. I'm sorry. That's better. Now, I want to, before I start stating some results, I want to make some general remarks on H principles, which somewhat came up before, but I want to get them out of the way. So,
This kind of similarities are generic in one parametric families or also in higher parameter?
no, they are not generic in higher parametric families. So this is a good question. So when you take a two-parametric family of even functions to R, you see other singularities. So they are not generic. Yeah. So and there's some classification up to some 10 parameters or something. So you can classify them and find local models like what you find in a 7-dimensional family typically. And it's getting more and more complicated. Mm-hmm. Okay, so first of all the H principles will hold relative to some open subset in this neighborhood of some closed subset in the source name. So I will not mention that. So whenever I state some H principle, it will hold in relative form. Also, all the H principles will hold in parametric form. In the K parametric form. There, maybe I want to say a little bit about it, how to formulate parametric H principles. Now, of course, the one way would be the Dani way, just adding in some invisible color some little z's everywhere, and this would be one possibility. So just look at. Let me maybe also say in general, I would maybe even consider some fibration x over v rather than the trivial one v times w. Yeah, so let's say we talk about x to the r would be the R-jet space on v, and you could just work and multiply everything with a parameter space, say some k-dimensional disk. And just carry along parameters with all the constructions. That would be some of the straightforward way to talk about a parametric H principle. Another way would be to talk about a fibered H principle. What does that mean? That means we take x over v, and we assume that v is itself fibered over another base space B. So that, say, if this is n-dimensional, I take this n minus k-dimensional. So the V itself looks like this. So it has k-dimensional fibers, and I will just talk about some things about sections here being, or sections in the R-jet space being holonomic or non-holonomic in this setting. But then I should, when I take derivatives, we take derivatives only along the fibers. So we take derivatives along the fibers only. And then this is doing the same thing. You think of this as a parameter space, and the fibers sit over this parameter space, possibly even in a topologically non-trivial way. And I'm restricting my functions to each fiber, and I'm taking derivatives of that restriction. And that will determine my R-jets. So this, I'm taking fiber-wise R-jets. I'm not taking derivatives in the direction of the base space. Yeah, that's just a little bit more fancy way of saying the same thing as parametrically. Now, once you are here, you can also say, okay, it's a fibration, you can even generalize a little bit further and talk about foliations. By saying, okay, I don't care that this is a fibration really, but I just say my V carries F a k-dimensional foliation. And then I can still take and over V I have X, I can take the RJet space, and here I should really then maybe give it some index, the foliated RJets. Again, I restrict now my section here to one leaf, and I'm taking derivatives only in the direction of the leaf. And then again, that's a yet more general way of talking about parametric versions. So at some moment I will maybe spell out an H principle, what it exactly says in this language. But oftentimes I will just not worry about the parametric form, because it consists in this language, it consists basically in the end just taking a different color and putting some curly F's everywhere. And then that's doing the job, yeah? Okay. And the last general remark I wanted to make, which also came up in Dani's proof of the H principle of polynomial approximation, you can reduce it to a local situation. So the proof reduces to the case where V is the n-dimensional cube, where I is an interval, you take the n-dimensional cube relative to the boundary. Yeah. Once you can do that, you can somehow work yourself inductively over the skeleton and so on, as explained in Dani's proof of the polynomial approximation. So I will usually also skip that step and only explain how it happens in the local model over a cube. Okay, so these are just some general remarks to get some out of the way. Now, so now I can finally define what wrinkles are. So let's start with the standard wrinkle. Depends on some parameters we want to see. So the W indeed depends on a dimension of the source space, on a dimension of the target space, and on some index. I would usually drop that. So this is a map from Rn to Rq. So this is a local model of a map having some very specific singularities, and we'll work out what singularities they have. So we have, it goes from Rn to Rq, but I will split Rn as R Q minus 1. This will be my coordinate y. R, this will be coordinate z, and x will be Rn minus q. And it's mapped to Rq, which I will split as Rq minus 1 times R. So this coordinate is still y. So the wrinkle is also a kind of a map which has only singularities of corank at most 1, because in Q minus 1 coordinates it's already just the identity. And here is something very similar to what I have probably hidden behind here. So let me rewrite it. So we have z cube. Now I want to write 3 norm of y square minus 1 times z plus the quadratic form, and the quadratic form should have index s. This would refer to the index here in this indices here. So this is the definition. So let's work out its Tom Boardman stratification, and I'll draw some pictures of this. So my goal today is basically to understand what the standard wrinkle looks like, and then tomorrow we can worry about some H principles about that. Okay. So what is this would be the whole critical set. Now, this can only be of co-rank 1, yes, because of this Y here. So what is it? When can it be of co-rank 1? It can only be of co-rank 1 if the derivative of this guy here with respect to the other variables, namely Z and X, vanishes, right? Now, the derivative with respect to X vanishes means that X vanishes because it's just a quadratic form, yes? And this derivative, let's just work it out. So the derivative is 3 times Z squared plus Y squared minus 1. Okay? We take derivative with respect to Z here. So this is, if I call this last coordinate U again, then this is del U over del Z. So this must be 0. So which means that Y squared plus Z squared is equal to 1. I can start, maybe I should reserve one word to try and make some drawing here. So questions? No? Okay. Okay, so this is a singular set. Now over this singular set, I need to understand when does this map have again not maximal rank. Now this singular set has dimension q minus 1. So this is really the boundary of a q-dimensional disk, right? Because this is what? Yes, it's a boundary of a q-dimensional disk. This is q minus 1 and 1. So it's in RQ, and you take the unit disk and you take its boundary. It's a unit sphere. Yeah, so it's SQ minus 1. So it's dimension q minus 1. Now, what do we do in the Tom Boardman classification? We restrict the map F to this one, and we map it again to RQ. Right? So in this second step, now we are already in the situation where the dimension of the source manifold is smaller than the dimension of the target manifold. So the rank drops if you have kernel here. Right? And the rank drops by 1 if you have a one-dimensional kernel. Now, turns out the kernel can only be one-dimensional, and what can be in the kernel? So what is the kernel of this map? Let's just the kernel of this map on the boundary of this sphere. You see, in the kernel, you cannot have any derivative in the y direction, because if any component in the y direction, then it's not in the kernel of the differential. The only thing that can be in the kernel of the differential is if you take derivative just straight in the z direction. So the direction of the kernel, let me maybe use a different color, is always this one. So this is the kernel of df along sigma of f. Yeah, I mean, away from sigma of f, we don't care, but along sigma of f, this is the kernel. Okay. Now you see that for most of so this is sigma of f. Yeah. This is a singular set. So for most of it, the kernel is transverse to sigma of f, which means if you restrict to sigma of f, then there is no kernel. Yeah. The only places where there is actual kernel when you restrict is here. So this here is sigma 1, 1 of f. And you can check it's actually sigma 1, 1, 0. So somehow third derivative doesn't match here. Yeah. So
We also just see the kernel is transverse to that equation.
right. Yeah. So this is what it looks like. Now let me make sure we understand a bit better what is going on now. So this shows that it has really only folds and cusps. So this is folds. So this is, if I'm away from the equator, this is just consisting of folds, and this is just consisting of cusps along the equator. Yeah. So this is a sphere of dimension q minus 2 now. Okay. So how does this set map into RQ? Now this I need to work this out, but the picture is, it looks like this. The image of this sphere is something which has cusp edge here. The picture looks like this. Now I want to do one more thing to this picture, so that will be important. If we restrict ourselves to some fixed value of y, and we look at what's happening as we traverse this from bottom to top. So what does this look like here? So then this is just a function of z. So z is being mapped to, well, we're at x equals 0, so I can forget about this one. So it's z squared, z cube plus 3y minus 1 times z. Now, and this depends on the choice of y. Now, this is now fixed. So I'm doing it over some fixed value of y. I'm looking what is going on there. Yeah. And we see that this is looking like this one-dimensional picture of birth death of critical points in Morse functions in one dimensions. Yes. So this is a function just of z with parameter, which is this one. So when this one is positive, what does it mean? When y is bigger than 1 in norm, we're outside of this sphere, then this has no critical points. So outside of that, it's just moving, and it's moving straight up in the. So this is our u, right? So it's outside. It's just moving up here. Okay. Now, at some moment, when norm of y. Okay. Well. So, I'm doing it wrong. I want to say here the y is in norm smaller than 1. I'm looking at the inside. I can also do it outside. So outside here, y is bigger than 1. It's just moving straight up. Nothing happens. If y is in norm smaller than 1, then we have this picture of a pair of critical points, and we know where the critical values lie. They must be in the image of this sphere, because that is the critical set. So what will happen is it will go here up, it will go down, and it will go up again. Yeah. Now, you see, now it looks a bit singular because I have projected out. Yeah. So if you added another coordinate, you would see this kind of behavior of the function. But now everything is happening on one line. Yeah, and this happens everywhere here. So and the way to think about this wrinkle, we're only going to be interested in the wrinkle in a small neighborhood of this ball. So we're only going to look at it in a small neighborhood of this set. And we're going to somehow say that we call a wrinkle if we find that in some map. Then we call it a wrinkle if we find the neighborhood of this set. So you should think of it, we're only starting very closely to, so this is rather small. So when we go inside of here, then we start somewhere here, we go up, we go down, we go up. Yeah. So here. But then at some moment it starts traversing this, and so this is what it looks like.
Do you mean that you will be interested only in a small neighborhood of the ball?
Of the ball, in fact, yes. And it will be important that we keep track of the ball. Yes. So the question, we could only be interested in a small neighborhood of the sphere, of the boundary sphere, because that is a singular set. But we want to keep track of the fact that we also have its filling by this ball. You see, because otherwise I want to see these whole pictures here of this one-dimensional wrinkles. And this is what I promised you with all these pictures. They are now, if you look at this picture, this is really a projection of this one-dimensional Morse function. Yeah. And I want to somehow keep track of this whole thing. If you only looked at the neighborhood of the sphere, you would cut it up here and here, and somehow you lose that information. This, okay, so this is one way to think of this wrinkle. It's a family of one-dimensional Morse functions in this variable z, parameterized by this other variable y. And when y is outside of this ball, they have no critical points, they're just regular functions. And inside, they have this particular, they have a pair of critical points. Actually, I can also say what the index is. The index is, remember, we have some quadratic part in the x variable, which is never appearing in any of the pictures here. But this is some quadratic form of some index s. Now, if we are here, then the index is just this index s. Whereas here the index is s plus 1. Because we have another index 1 now from this z variable. Yeah? So, okay. Now I already mentioned the case.
So in this picture, the Y's have two, there's two dimensions, right? In the Y, it's like a plane.
The y, yeah, in my picture, y would have two dimensions.
Yes.
This would be y1, y2. Yes. I mean, you can do it with one dimension in y, then it's just a planar picture, and you still somehow see the essence of this behavior. Yeah. Right. Now, let me mention the special case of a function. Maybe I can leave it in here. Q equals 1. So we're just looking at maps now from Rn to R. So there's no x coordinates. So there's no y coordinates. Yeah. Because the y coordinates now live in RQ minus 1, so they're not present here. So the function is now just mapping zx to z cube. Now there's no y coordinate, so it's minus, there's a formula, minus 3z. Yeah. That's true. And now this is all we see. And now what does this whole wrinkle look like? Now there's nothing in Y to draw, so we only see this one picture. So we only see this picture of a pair of critical points of index S plus 1 and S, but they are connected by some, you can think of it as a gradient trajectory for some gradient like vector field. Yeah. So this is now our wrinkle, which is just a pair of canceling critical points of index S plus 1 connected by a gradient trajectory. And we want to keep track of this whole object. We want to view this as one wrinkle. Okay. So
Do you really mean canceling?
well, I mean canceling in the sense that well, yeah, you okay. Well, yeah, I mean you can cancel them, right? But you could cancel them if you somehow could continue this further down. Yeah, this is some other.
This
Yeah.
point will be crucial.
Yeah, this
in the
point. Yeah, so
construction we'll do.
that I should not say canceling. Yes. So if but okay, let me maybe comment on that because this is a crucial point. So if this wrinkle were part of some function here which extends further like this, then I could cancel this whole pair of critical points and not change it outside. Yeah. But the problem is that to cancel this is I need to affect the function elsewhere, and it's not a local operation. It's not something that I can easily do. Yeah. Okay. So this is indeed, and this will be crucial. That precisely they are in canceling position. They look like you want to be able to cancel them, but you may not quite be because the wrinkle is only giving you this little bit of it. Yeah. What it does show is you can create wrinkles, yeah, and creating wrinkles is just doing this. Yeah. You see a beautiful wrinkle like yeah. Just somehow you see a double fold here and it's disappearing to the two sides. Yeah. So this you can create them out of nothing. But and of course the wrinkle that you created you can also remove again if you want. But a wrinkle which comes to you just with this bit of information, you don't quite know how to remove. Thank you for this. This is probably. Let me add one more bit. Do you have still a few minutes? Yeah, I just wanted to add one more thing which will be important. We can now, if we look at the differential of this one, this is maybe one thing I still wanted to write down. So what does the differential look like? Well, we first have an identity matrix here of dimension q minus 1 in the y coordinates. So this is y, this is y. Yes. Then we have nothing here if we take differential with respect to z and with respect to x, and there's nothing here. Now, what do we see here? We see something which I don't care. Here, with respect to x, we just see plus minus 2x, something. And here's the interesting part. So we already computed it. We see the z derivative of this function here, which is this guy. Okay. Now this differential does not have maximal rank q precisely where this vanishes and this vanishes. Right? Okay. Now, if I can make this somehow non-zero, it will have maximal rank. So what we're going to do is we're going to replace this by some function, no matter what it's called, let's call it gamma. Rn to R, such that gamma is equal to this outside the neighborhood of this q-dimensional disk where all the interesting stuff happens, because outside this function is already positive. Then this expression is positive. Yes. Now inside, as we cross the boundary of this ball, this becomes negative. And on the boundary we have 0, and then the rank drops. Now what we're going to do is that we're going to make that gamma is positive everywhere. So we just replace this function, which becomes negative as we cross the sphere. We just raise it and make it positive over that sphere. Okay? And then this is always a positive number. We have an analytic matrix there. And then the rank is going to be always maximal, namely rank Q. And then we will call this the regularized differential. So this will be an epimorphism, meaning a linear surjective map from Rn to Rq at every point. Yeah, because we go next time tomorrow we're going to state an H principle for submersions with wrinkles. So which are everywhere submerged except that they have some wrinkles. But to state an H principle, we want to look at the formal data. The formal data of submersion is an epimorphism. So we also want to associate to a wrinkle that formal data, and this is the way to do it. Yeah, you just replace this by some positive function, and then you have associated to it an epimorphism, and that will be the formal data that we associate to a wrinkle. And then tomorrow we are ready to talk about an H principle. Okay, thank you very much.